How do engineers properly bias transistors in analog circuits? Imagine trying to keep a delicate balance on a tightrope. That's what biasing a transistor in an analog circuit is like. It's about setting the right conditions so the transistor works just right. When a transistor is biased properly, it stays in the active region where it can amplify signals smoothly. If it's biased too much or too little, the output gets distorted or the device stops working. So, how do engineers make sure this doesn't happen? They use specific methods to set the right voltages and currents at the transistor's terminals. First, they focus on the operating point, also called the Q point. This point is defined by the collector current and the collector-emitter voltage when there is no input signal. The goal is to keep the transistor in the active region during signal changes, avoiding cutoff or saturation. For silicon transistors, the base emitter voltage is usually about 0.7 volts when forward biased. Next, they ensure the junctions are biased correctly. The base emitter junction needs to be forward biased, meaning the base voltage is higher than the emitter by about 0.7 volts. The collector base junction should be reverse biased, which prevents unwanted current flow during normal operation. To achieve this, engineers choose a biasing method. The simplest is fixed bias, where a resistor connects the base to the supply voltage. This provides the base current but is not very stable because it depends on the transistor's gain, which can vary with temperature. Another method is collector-to-base bias, where a resistor connects the collector to the base. This creates negative feedback, making the bias more stable as the collector voltage changes. Emitter bias is also common, where a resistor is placed in the emitter leg. This resistor creates negative feedback because, as the collector current increases, the voltage across the emitter resistor rises, reducing the base emitter voltage and stabilizing the current. The most popular method is voltage divider bias, which uses two resistors to form a voltage divider that supplies a stable voltage to the base. This method is preferred because it maintains a consistent bias point regardless of transistor gain variations. Once the biasing method is chosen, engineers calculate resistor values carefully. They use Kirchhoff's voltage law and the transistor's parameters to find the right resistor sizes. For example, if they want a specific collector current, they determine the base current by dividing that current by the transistor's gain. Then, they select resistor values to supply this base current at the given supply voltage, considering the base emitter voltage drop. To keep the bias stable over temperature changes, they include emitter resistors or feedback mechanisms. As temperature rises, the transistor's parameters tend to shift, which could cause the collector current to increase uncontrollably. The emitter resistor helps prevent this by providing negative feedback. When the collector current tries to rise, the voltage across the emitter resistor increases, which reduces the base emitter voltage and keeps the current in check. Proper biasing is essential in many analog applications. It ensures amplifiers work linearly, whether in audio systems, radio receivers, or sensor circuits. Without correct biasing, signals can distort and devices can become unreliable. In summary, engineers bias transistors by choosing a biasing method that offers stability, calculating resistor values precisely, and adding feedback or emitter resistors to counteract temperature effects. This careful process keeps the transistor operating in the active region, ready to amplify signals accurately and consistently.